I'll just give it a couple more minutes and then we'll stop.
Is that light? That's a lot of light.
Yeah, we can shut the blinds.
Then don't show a secret. Get coffee now.
Can you tell them that the speaker light is not just speak in the microphone? There's a light up there. Just say, Phil, can you turn the, here it is, okay.
Hello? Oh, yeah. I can see it. Oh, okay. Don't look up. Before we start in a minute, just a reminder that we also have coffee and tea after the talk. So if before we only had before the talk, now we have before and after. So, so you have a chance to chat with the speaker afterwards. Oh, and we also have a couple of spots remaining for dinner. Early dinner at 5 p.m. in La Royale, which is a new Peruvian restaurant here. So if anyone wants to join, please come by. It's first come, first serve, but yeah, it's very good. Yeah. Okay, I think we probably can start. Yeah, it's good. I'm sorry. Yeah, it's 5 minutes. So, the rule. My name is Julien Gordon. I'm a chair of Atomic and Molecular Physics Division, and it's my pleasure to introduce today Professor Julien David from MIT. Just a brief introduction to Julien. Of course, a lot of you know him at least by name because he was involved in the discovery of the TRAPPIST system and led the characterization of all 7 planets' atmospheres there. So, he's of course famous for this research. I think he started as an aerospace engineer at the beginning at Belgium, and then he got interested in exoplanetary science, and he did a number of degrees, which I cannot read all of them, in University of Liège. And in 2011, he came to MIT, and in just 3 years, defended his PhD thesis in 2014, and then stayed as a postdoctoral fellow there, and now he is leading Disruptive Planets group at MIT. It's great to have Julien here to speak to us today, and please, Julien, welcome to.
Is the mic on? Yeah, no? Okay, good, great, awesome. Okay, well, thanks for having me here. I realize it's been a while since I've been around. I think the last time I came here was before COVID, so if you'll indulge me before diving into the specifics of what I want to talk to you about, specifically the limitation of the stellar models we're using in exoplanetary science, as well as the opacity models to tie into some of the great work that's done here by Julien and the Hydron and Hydron group. I'll give you a quick update on what's been going on down the river with our group. So I won't give you details of everything we do, obviously, but just an overview so that you understand how it ties into the specifics of how to characterize these objects. So the group is called the Disruptive Planets Group, and our goal is to discover and study worlds that are new and really use them to disrupt, to consolidate our understanding of planet formation, but also hopefully habitats in some point. And so in order to get to that point, we have an ensemble of projects that fall into 3 quests. A quest that's about discovering new objects, and I'll unpack that in a few minutes. Then really developing the technique to characterize them, and ideally make the best of the multi-billion-dollar facilities we have now. And then once we have that, we can do some contextualization, meaning using these in-depth exploration of some of these worlds, or zooming out and getting a meta-level perspective to use a large sample of well-understood objects to reveal new physical processes, say underlying planet-star, tidal, or heating interactions, for example. So in the Discover quest, connecting to the TRAPPIST-1 discovery, we've built in 2018 the first Speculoos-class telescope in Tenerife, so in the Canary Island. And Speculoos is a parent project to TRAPPIST, which was a 60-centimeter telescope, a prototype that led to the discovery of TRAPPIST-1. And so that telescope aimed at about 50 M-dwarf to lead to the discovery of TRAPPIST-1. Speculoos is going for 1,000 of them. And so far, we have completed the analysis or the monitoring of about, just under 1% of them. And there's some for which it's still ongoing. Quite a few have been untouched. So it's an ongoing search. And so in this quest, what I started to do with my group is use some of our time to discover other planets of potential interest, such as Pi Earth. I mean, that's the ugly name that it had on it originally. And we rebranded it as Pi Earth, owing to the fact that it has a 3.14 days orbit, which really helps the student get PR every year, every March 14th. So that was really great. And what you see here is, and I'll get back to a plot like that later, the expected amplitude of the spectrum of the planet as a function of the equilibrium temperature. At the top are the planets the most favorable in the temperate regime, which are the TRAPPIST-1 planet, and that one fare relatively well, but it's not as exciting in the TRAPPIST-1 planet, and that's okay. But what you may know is that in our fields of view, there are many more stars than the star of interest. So in this field of view, observed with Speculoos, compared to TESS, you can see our target, the M-dwarf, which is upon which most of our science is based. But what I started to do is develop a pipeline that leverages the about 2,000 other stars that we have in the field, which may have a really high scientific potential. Even though TESS has been an all-sky survey, you can see that the pixel size of TESS, same field of view, is so big that all of those stars that may have, say, a Neptune-sized planet of interest are like unmonitorable. So we cannot really leverage the data from TESS for these fields. So we have about 2 million field stars that we can leverage in comparison to the 500,000 that were in the nominal TESS mission. And then building upon that, we've started to leverage GPUs to search for asteroids that are passing in the field. And I won't go into the details, but if people are interested, you now know about that. We also do that. We get down to magnitude 24 with our facilities, and we find these very faint, unknown objects. So these are the kind of things that we do in the Discovery Quest. The great thing of having our own observatory is that we can also, if students are interested in joining that, train undergrads to leverage this robotic facility. We've trained about 20 students so far. And most importantly, because we have this relationship anchored not only in research but also in education, we've managed to revamp a landmark offering that MIT had for a long time. The MIT Astronomy Field Camp started in the 80s but died during COVID. We were sending about a dozen students every year to Lowell Observatory. Relationship changed. And so for a few years, we were without any field camp. And now, thanks to Artemis, we can send students to Tenerife every January for 3 weeks of hands-on astronomy, which really help deepen the kind of relationship we have with our colleagues in Tenerife. So that's a brief overview of that part, contextualized we pretty much do maps of exoplanets, study the transient heating when we have an eccentric orbit. That helps us constrain the radiative and convective timescales of atmospheres. And we also get to study planet-star interaction, where we get to see pulsations of the star that appears to be harmonic of the orbital period. So that tells us about specific modes of interaction between the planet and the star, which affect their migration patterns. So that's more of the zoom-out, meta-level understanding of these objects. I won't get a chance to introduce everyone in the team, so I decided to just put a slide so you get to see the different faces and names. These are the current long-term members of the team. None of what I'm presenting will be possible without them, obviously, but not everyone is going to get slides today, so here are their faces. All right, characterization. Now that we have found objects and we try to really get to a deeper understanding of what's going on in this system, how do we study, characterize them, and how can we do that with a high enough precision without compromising robustness of our inferences? So to set the scope of this talk, the setting is as follows. We are entering an era of increased information content. Right? We have these multi-billion-dollar facilities that are of this bigger aperture, broader wavelength coverage, higher resolving power. And so can we keep on doing what we've been doing so far and expect to have robust inside? Obviously, the answer is no, and I'm going to unpack that because we have to pay attention to the reduction techniques. I won't go into that. I'm going to focus just about model fidelity, specifically about the model fidelity of opacities and stars. I realize that it's a broad audience, so I sneaked in an exoplanet refresher first. So how do we do what we do before going to the details of this model-driven bottleneck? Once I've done that, I'm going to zoom out and talk about the next step towards inhabitability assessment in this decade, and then how we can use those understanding to set up, say, a roadmap for a TRAPPIST-1-like system with James Webb. Also, if you have questions, let's make this interactive. Like, I don't have 1 hour of chatting, so I have about 40 minutes. So if you want back and forth, you can totally do that. Okay. All right, so exoplanet refresher. Why do we care about exoplanets for those that are not doing that? Yeah, there is the whole thing about finding life elsewhere, which is kind of cute. But everything we know about planet and planet formation has been based on one unique sample, the solar system. So even though we know relatively well, I won't say that we know Jupiter perfectly, there's still a lot of work to be done, this is still a unique sample, right? It'll be like trying to forecast or predict the outcome of a political election by asking different humans, but they are all from one same family. So to some extent, they do share a history and value. They may not vote for the same person, but still they do share some aspects. These are an ensemble of planets from around one type of star at the same time. So it will bias our understanding of planetary system and formation. For example, just the concept of Jupiter-like planet being far away from the star was challenged with the first discovery, a gas giant orbiting its star within a few days. Right? But that's not the only example. Since the field really bloomed, we find planet without star, free-floating in the galaxy. We found planet with multiple stars, offering this iconic double sunset like Tatooine in Star Wars. I think by now, the maximum number of stars in the system is 4, which is pretty good. We found planets with multiple rings like J1407b that should have about 37 rings, about 200 times the extent of Saturn's ring, so big that if it is indeed the case, it will be bigger and brighter than the moon in the sky if Saturn had such a ring system. And we found planets just dying around their star, being pulled apart by the gradient of gravitational field that's around a white dwarf. So to give you quickly an understanding of the diversity of planets we found and how disruptive these discoveries are to our understanding of planet formation and evolution, which is great. So not just life. And so how do we get to make these discoveries? When I think of planet, maybe you too, I think about the rings of Saturn, the bands and the zones of Jupiter. Yeah. Remember I showed you quite a few cute little posters for exoplanet? There's a reason for that. Because when you think of exoplanets and you look at a system, unless it's directly imaged, the only thing you get is this nice bright dot on your detector with a few pixels. So everything we do It's like magic. It's leveraging data science to extract the contribution of each of the different components. Obviously, the flux vary with time and wavelength, which gives us the core techniques for discovery. Radial velocity looks at how the flux of the star shifts through a Doppler effect, giving us the periodicity, so the period of the planet, as well as the mass, technically the projected mass. I won't go into the details. And then the other technique, looking at the flux variation as a function of time, gives us the transit when a planet passes in front of it, and the planet-to-star area ratio relate to the transit depth, so we get the size of the planet. And in some instances, over the years, so first planet detected here was in 1995, here 1999, and so from that point on, we had a few planets for which we had mass, radius, so the density, so we can start talking about bulk, composition. Quite a step forward, not just stems with the size or stems with a mass. And then the real leap forward from my point of view was when we started to be unable to study the atmosphere of those worlds, because when they pass in front of their star, there's a tiny fraction of light that's going through the planetary atmospheres and is imprinted, that allows for the stellar spectrum going through that ring to be imprinted by the atmospheric features. And that's transmission spectroscopy. What does it look like in practice? If we have an atmosphere that is opaque on at wavelengths and transparent on other, the atmosphere is going to contribute to the flux drop, leading to a slightly deeper transit depths. And this variation in transit depths that are, second order, allow you to probe the atmosphere of the planet. This is a spectrum from 2013 of Hubble Wi-Fi Camera 3 monitoring of the hot Jupiter 209. And you can see that the transit depths increase around 1.4 micron. So the scale, that's about one scale height for the atmosphere here, so about a percent in increase. And that feature is from water. Okay, so that's the kind of thing that we could do for the last 10 years. But things are changing dramatically now that the James Webb Space Telescope is coming online. So what is new and what is next is everything that can be enabled by facilities like this one and the ELTs we just heard about earlier during the lunch talks. So what changed? Exquisite data quality owing to the collecting area, much bigger, higher spectral resolution, and most importantly, not most importantly, but that's also important, a wider spectral coverage. Why? We get to detect more molecule owing to their fingerprints, but also the relative intensity of different feature of a same molecule has information about the temperature and pressure profile that you can't get if you only have one molecule, or not that easily. So, we're moving from seeing the universe in CRT to seeing it in 4K, literally, and pictures are great, but for people in the room, I think that what matters most is the spectra. So I'm going to skip this cute picture to focus on this first detection of CO2 in the atmosphere of an exoplanet. What you have here is, again, the transit depths as a function of wavelength, and this big peak right here is CO2 detection. So how does that compare to what we knew before? This is the same planet, and all the data we had prior to James Webb coming online. This is the water feature I showed you before for HD 209. And pay attention to this part of the spectrum. I'm just going to add in what I showed you before coming from James Webb, so you can appreciate the jump in information content. Same CO feature, these are models at the back, data of course, and you can see the precision, the 1 sigma error bar, increase, well, the error bar decrease, so the precision increase significantly, despite the fact that we have a much higher spectral resolution, and we can really map this feature with high precision. Okay, so that's the jump into a new era we're experiencing right now. And as this is happening, for context, in 2013, 50% of my PhD work was on, breaking down the analytics of transmission spectroscopy and understand what is the information that's truly stored in there in such a way that what can we independently and this robustly extract from the next generation of transmission spectra was what I was really excited about. And looking at the analytics, I got a sense of what we could extract, but all of that was relying on the fact that we actually knew how light and matter interact, right? If we don't know that, then we can't decode, we can't transcribe the spectra. And so after doing that work, we started to transition towards understanding what are the limitations of current opacity models and how these limitations propagate down to our inferences. So why is that important? Because when we have a transmission spectra, what's truly behind that are four pillars. A star that produces a photon that goes through a planetary atmosphere, and how the light interacts with the planetary atmosphere is defined or guided or ruled by the opacity models. And then these photons come onto our instruments and are collected. When we do inverse problem, we do need to model all of that chain of event in order to decode what is actually happening and constrain the property of each of these elements, all right? So until a couple of years ago when GEM was coming online, this was completely instrument dominated at the noise budget level, all right? So the instrument was the bottleneck of our characterization. But that did get upgraded. So what happened to the rest? Is it still good enough for what we hope to do? And the answer is no. I'll give you an example of what was published in 2020. People looking at how the assumption we made on the topology or the structure of the planetary atmosphere affect our inferences to get us going about, to think about how things may affect our data when we look at star and opacities. So what was done by Ryan McDonald et al. In 2020 was to acknowledge that up till now, we were assuming that the atmosphere of a planet had a uniform terminator. So you could use a 1D model and say, that's good enough to represent the composition, temperature, and pressure profile all around the terminator. But we know that most of the exoplanets studied, for which we can have a good enough signal-to-noise ratio, are close to their star, so they are tidally locked, meaning that the west or the evening terminator is going to be hotter than the morning terminator that's come from the permanent night side, right? Tidally locked means that they have a permanent day side and a permanent night side. So what happens when we account for the fact, generating synthetic data, that this is truth, and we retrieve on the property using these assumptions? And what they found is that, bear with me, forget everything on the left. We don't have to go into that today. Focus just on the ultra-hot Jupiter case, and notice that we're not even talking about James Webb level data. We're going to do this example with Hubble quality data. And what you see is that on this plot, what you use to generate the data is quite far from what you retrieve, right? So you use an evening and morning terminator, but you use a uniform terminator to retrieve, and you retrieve a temperature that's 1,000 Kelvin lower than what you actually use. So you have a significant bias over 5 sigma on the temperature retrieved, which affect other properties such as the number density that you retrieved on, say, your water abundance to compensate for the temperature that you retrieved here. So that's the kind of work we're interested in doing and that we're doing in parallel, focusing now, because we can upgrade that, right? It's relatively easy to say, all right, my atmosphere is more complex, let's just increase the number of parameters and make it more real. Cool. What about your opacity model? Like, how do you do that for opacities? So we ask ourselves the question, what happens when we start scratching the surface of opacity models? Can they still hold this data quality? So this work is done with quite a few people from here, though that wouldn't be possible without you too. And as I said before, I was aware of the kind of information we can extract. So that's work that I was doing during my PhD in 2013, looking at the kind of information we could extract, assuming we know opacities well. That's synthetic James Webb data, and we can retrieve with high precision number density of a wide range of molecules, constrain the scale height, so the pressure profile, temperature, and so a lot we can do if we crack the code. Why? I'm going to skip all the analytics to focus on one thing. Because the apparent size of the planet in transit is a function of how the number density, the temperature, the pressure change with radius, number density being stored on its own, temperature and pressure being stored through the cross-section of each of the element. I is for all the different elements. So when you unpack that, you can show, and that's what's great, I'm going to skip all of this, that depending on the regime you're observing, this simple formulation of the apparent size of the planet store all of these pieces of information, the scale height, the number density, these different coefficients that are a function of the broadening effect and the pressure. Each of these different values are stored in a different way, encoded in a different way, allowing you to break the degeneracy if you observe enough of these extinction processes in your spectrum. If these dependency to the core physical property of the atmosphere were about the same, you wouldn't be able to extract their individual contribution. Because of each of these different extinction processes storing the data differently, you can break that degeneracy and really get constraint on each of these properties, which is what we want. But again, that is possible only if we really know all of this. So we looked around and realized that that's not new. Exoplanetary science is a lot of things that we think we reinvent, but solar system science have already done that 20 years ago or so. And this is a great example where back in 2005, the discussion around the extent to which the abundance of oxygen and really water can be characterized is dependent on how well we know the line profile of water. We're basically facing the same kind of limitation, and I'm going to highlight that. How did we approach that problem? We took the same framework as I showed you before, and we took opacities out, and we asked ourselves, what do we know, what don't we know? So instead of, if you think that each of these blocks are a multidimensional parameter space where truth lie, instead of considering that truth is here for opacity model, we ask ourselves, what is the confidence interval? If one dimension is to what extent do we know pressure broadening, instead of saying it's a Dirac, we really know that well, we looked at how poorly constrained that is, or well constrained. I'm attacking no one here. Just what is the level of uncertainty or confidence around that? And we perturbed our opacity model to such an extent that instead of having full confidence in our model, we start having a certain level of noise around our opacity model. And then we did an ensemble of retrieval, not considering that we know truth, but understanding that there is this level of uncertainty to look at how this confidence interval propagates onto the atmospheric properties we were retrieving. And that's what it looks like. I'm going to explain one of these panels, but what you see here, before I dive into the details, is how well we know the base temperature, the profile temperature, the number density of N2, and so forth, for different perturbed cross-sections. So it's a sensitivity or perturbation analysis, if you wish. I'm going to zoom in on the number density of CO2 for one of the synthetic planets we found. And so what you see here is the confidence interval for the same data set for different opacity models used. The data used to generate the synthetic spectrum is the dotted line. It's not that I'm shaking, that the pointer is fine. I'm sorry that you see this like all over the place. I can try to just be more precise with this, but long story short, you see the scatter? What does it mean? Well, the scatter relates to the opacity-driven uncertainty. So when we perturb the opacity, say, to account for different ways of broadening, of parameterizing broadening parameters, we go from the default cross-section in red. Default doesn't mean it's true. It means that this is the one we use to generate the data, to the one in blue. You see this shift is related to how we've modeled broadening. And so the shift here is using exomol. The shift there is using high temp and so forth. Versus the precision of the instrument. The narrowness of this interval, which is somehow consistent across these different retrieval, is related to how well the instrument can perform. And so the takeaway message is, while in our synthetic data sets, we should be able to retrieve with high confidence the, say, number density of CO2 with a precision of 0.2 dex. The uncertainty stemming from how well we know opacities propagates to an uncertainty on the retrieved parameter to the level of 1.1 dex, which is significant, which is why we call this an opacity-driven accuracy wall. And to put this into perspective, this is how well we should be doing with the synthetic spectra we generated or synthetic model we were using. This is how well some cycle 1 programs or JWST were hoping to constrain the number densities of some of the atmospheric elements. Right? So forget this axis, it's irrelevant for this talk. What matters is really the y-axis, the precision with which we can constrain the atmospheric parameters, which seem to be capped at the 0.5 to 1 dex owing to the current state of opacity models. And I'm going to contextualize that a bit further using true JWST data in a second. All right, before I move to a real case scenario, I want to add something to this. In astronomy, we tend to build confidence in our results by looking at our residuals. If our residuals look pretty neat, then the model we're using should be okay. It is not always the case. Why? Because if we have this biased value, it is because the atmospheric parameters can find a way to compensate for the perturbation we've caused in the opacity models. And so having a good fit doesn't mean that the models we're using are actually good enough to do what we're doing. And so we should be worried. We should not use the usual strategy of saying, fits are great, so everything I'm doing is fine, my inferences are robust. There can be compensations owing to the dimensionality of the parameter space you're using. Great, so what does it look like in real life? We moved on and used the real data from WST39, so it's the same spectrum as I showed you before, just our version of the spectrum. And we proceeded doing perturbation analysis, accounting for the fact that, believe it or not, this feature, CO2 feature in a hydrogen-dominated atmosphere is really, really difficult to constrain because we actually have pretty much close to no knowledge of how CO2 is broadened by H2. Surprisingly enough, this feature is going to be studied greatly because most of the planets for which we're going to do transmission spectroscopy are going to be gas giants, and that feature is going to be a landmark, and we actually don't really know, again, how CO2 is broadened by H2, so we ask ourselves what happens when we account for this lack of knowledge. And surprisingly enough, nothing happened, and that was a shock. Remember how before each of these perturbed confidence intervals were inconsistent with one another? They were consistent here. So we ask ourselves the question, why is that? Well, in order to answer that question, I need to tell you what was the dominant contribution to, or factor, to this discrepancy between the different retrieved value. It was primarily our lack of understanding of cross-species broadening and far-wing behaviors, which happens in the relatively high-pressure region of the atmosphere. And so what we realize is that for those kind of gas giants, WST39, most of the flux is our contribution function that shows you where most of the flux related to the spectrum, or most of the information related to the spectrum, comes from in the atmosphere. These were the cases that we had used in our synthetic datasets for the first papers. This is Earth. So you can see that we're probing relatively deep in transmission, while for the data we were using now, we are probing in a much shallower part of the atmosphere where these two dominant contributors to the opacity-driven wall, opacity-driven accuracy wall, are not significant. So we could get to a point where we understood that for large, hot, metallic exoplanets, transmission spectroscopy should be mostly reliable with JWST, but not for everything else. So in summary, before I move to stars, we showed that atmospheric parameter can compensate for lack of opacity models in transmission data, so we should be worried of just relying on a great fit to say things are okay, inferences are robust. We highlighted that the compensations are leading to bias to within 0.5 to 1 dex, and so showing constraints as good as that should be done while discussing the sensitivity to opacity models. that for hot, large metallic exoplanets, things should be okay. But for all other, we should pay attention. And in fact, as I note at the bottom, when we're dealing with emission spectra, we should be worried for every single planet. Why? In transmission, you have a really long line. Well, the path through the atmosphere is much longer than when you do emission. So even for hot gas giant, in emission, you'll be probing pressure level where the issue I highlighted before will be relevant. So we should pay attention for all exoplanets in emission. And so what's next is for us as a community to move towards the next generation of opacity models. And in that context, with partnership of people here, as well as in Paris, we're starting to move towards a new infrastructure to perform quantum calculation to help us focus on some of the core system and alleviate this issue. Now, unless you have questions, I'm going to quickly give you an overview of what's going on when we start dealing with stellar effect, the lack of fidelity of stars, stellar models. For those who don't know, a transmission spectrum is based on the relative measurement of the flux of the system prior to transit and during transits. And so for a while, we didn't really account for the fact that the star is heterogeneous, which means that when we don't account for that, the actual light source, which is what the core is masking, is different from the hemisphere integrated spectra of the star. And so the relative measurements lead to not only the planetary fingerprint coming onto the spectrum, but also the stellar fingerprints. And so a transmission spectrum is not a transmission spectrum of the planet. It's actually a wrong name. It's a combined spectrum of both the planet and the relative measurements of the core versus the hemisphere average spectra of the star. And this is where things get tricky, which is why you're starting to see news along those lines. We found water, but we actually don't know if it's coming from the planet or the star. And this is going to be one of the other bottlenecks we're going to have to deal with, disentangling between what's what. As Julien mentioned, I was lucky enough to lead the exploration of the TRAPPIST-1 system with the Hubble Space Telescope. And so we're starting to move towards mitigation strategy because M dwarfs, the latest M dwarfs, really have a lot of these additional fingerprints, molecular fingerprints. What you see at the top is us trying to leverage the out-of-transit spectrum to ask ourselves, is what we see out of transit a star and just a photosphere, which is what's fitted here, a photosphere plus a spot, a photosphere plus a spot plus a faculae. So we're starting to ask ourselves, what's happening before transit? And then do we see a spot or a faculae crossing during transit? And if so, then we know what's what, what's the chord, what's the rest of the photosphere. And what we realize is that it's actually difficult to say what's what with this out-of-transit spectra. What you see in black is the HST data with the photon noise error bar. And then what you see as a spread is the ensemble of possible correction, where we correct for the photosphere plus a spot, plus a cold spot, spot and faculae, and so forth. And all of these corrections are consistent per what we see in the out-of-transit data. So we don't know to what extent and for what we should be correcting. In other words, we're showing that we have a spread, or we've moved from a photon-limited or an instrument-limited regime into a model-limited regime. But what could be behind us not being able to constrain the true level of heterogeneity of a star? Well, we started to think that it could be due to the fact that the extent to which we can model the spectra of M dwarf is really poor. You have real data from James Webb in black, best fit model in blue for a G-type star. We're doing really well. These outliers relate to an issue of calibration. I can talk about that later. But this is the best we can do in terms of fit for the TRAPPIST-1 spectrum. And you can see that in order to have, say, a reduced chi-square of 1, we would have to increase the error bar by a factor of 40. So that's how bad the fit is considering M dwarf. So we ask ourselves, could it be that us being unable to derive the true level of heterogeneity of the star relate to us not being able to model the emission spectra of each of these components? So we've done the same type of work as we've done for opacity model. We generate synthetic data, different level of activity, and use different stellar model to cross-retrieve and directly retrieve to see if we could then move beyond this limitation. I'm going to skip to get straight to conclusion. What we found is that indeed, if we have the right level of fidelity, there is a way for us to identify the true level of heterogeneity. So this is case one. We generate with only one heterogeneity on the spectrum, and we do retrieve one heterogeneity. Case two heterogeneities, we do retrieve two heterogeneities, and so forth. So in order for us to be able to correct properly for stellar contamination, we need to know what's going on in the out-of-transit spectra. In order to do that, we need to have stellar models that are of high enough fidelity. And if we do that, we can finally get to corrected transmission spectra where we've extracted the planetary contribution, and then we can move towards in-depth atmospheric study. Before that, not going to work. We're not going to be able to say if we're dealing with spectral features or hybrid features. That seems to be the only path forward. Which leads to the question, okay, cool. How do we get to the next generation of spectral model? A lot of effort is going on the theory side, where we start to account for 3D effect, magnetic effect, line of sight effect, and you can see already the differences from what we had before. You know, these differences between the 1D models of MPS Atlas, Phoenix, and the 3D models are orders of magnitude in some of the wavelength range, while we need to be able to rely on spectra precise at the level of a few percent to do these corrections. Okay? So we ask ourselves, okay, these models are there, and we know that when we move towards new theoretical models, we need to have data to benchmark them. Are there ways to get empirical constraints on these stellar models? And what we started developing is a framework of the rotation curve of a star to extract, owing to the time dependence of the contribution of each of these features, their spectra. And we show that indeed, using the James Webb Space Telescope, there is a way to move towards empirical constraint on the emission spectra of different components on the star. And so our hope is now to build data-driven libraries of the spectra of different heterogeneity on the star, so that we can use that to fit a different epoch for their contribution in the out-of-transit data that's high enough fidelity, and then we can get the spectra of the planets. So that's what we hope to focus on. And with that, 15, still have a few minutes, excellent. I'm going to tell you what's next. What's next for us, forgot that this was there, is to think of the TRAPPIST-1 planet and other systems like it, and go back to inhabitability assessment. As we heard earlier today, there's a challenge in looking for the typical biosignature, O2, for example. And so we ask ourselves the question, is there anything else we could do that could provide us with valuable insights regarding the habitability or the biosignature of these exoplanets? And I'll ask you not to share that. It's accepted. It's not published yet, so I realize that's live stream, but hopefully we'll find a way around it. What we realized is that we could, when we have multiplanetary system, leverage the apparent depletion of CO2 across a system to highlight the presence of either a strong water cycle that would lead to that depletion locally, or a strong biomass that could also play a role in the depletion of CO2. And so with James Webb, thanks to that habiosignature, as we call it, depletion of CO2 as a signature for possibly habitability or life, there is a path towards habitability assessment and possibly inhabitability assessment with the James Webb Space Telescope. I'm going to skip that as it's streaming online to go straight to, now that we know that and we get an estimate of how long or how many transits it would take to do that, we stepped back with a TRAPPIST-1 James Webb Community Initiative that gather over 80 authors on this roadmap, and highlighted the steps that needs to be taken to do atmospheric assessment for TRAPPIST-1 planets or TRAPPIST-1-like planets, characterize the stellar effect well enough to enable in-depth atmospheric study, and ultimately do these HAB signature assessment, and finally try to break the degeneracy if we do see CO2 depletion between strong water cycle and maybe even plate tectonics and or presence of life. And I'm going to summarize this here to make the point for why we do need, skipping that, why we do need to do that now, skipping that too, I can talk to you more about this. So why is it relevant to have this discussion about roadmap? Because in order to assess for the presence of an atmosphere in the planets, around planets like TRAPPIST-1s, we first should focus on the inner planets using emission photometry or emission spectroscopy. And I'm going to give you every single time an estimate of how many occultational transits we need and how many hours that corresponds to. So you get a sense of how long of a time scale we have and why we should get together as a community to start really thinking and intentionally planning ahead rather than just drifting from one cycle to the next without targeting key milestone. And that's we've done. Step one is on the way, so we're fine. If it happens that the inner planets are featureless, then we can use them to look for the presence of atmosphere around the other planet, because it happens that if you use multi-transit with one of the planets for which you know you have close to no atmosphere, what's happening during the transit is pure stellar contamination. So you can use back-to-back transits to help constrain the level of contamination on the following transit or the transit that just happened before. Why is this relevant? Because in TRAPPIST-1, close to 50% of the transits are within 5 hours in another transit. So there's plenty of multi-transit window, and that's actually what I leveraged with Hubble to try to increase our yield of transit by a factor of 2 per HST hour spent. If it isn't the case, then we really need to leverage what I was talking about, this rotation curve of the star, to derive the empirical spectra on the stellar component to enable atmospheric study. And that's another 80 to 100 hours of full rotation of a star. Once we've done that, if we find an atmosphere, going deep into the characterization of one planetary atmosphere is going to take 40 transits per planet, so about 200 hours per atmosphere. That's what you need to estimate the presence of CO2 and constrain depletion of CO2. Once you have that done, if you find a signs of local depletion of CO2 and you want to know if it's mostly due to a strong water cycle or, say, the presence of a conventional life form, I say conventional here, meaning that we connect that to the production of O2 amongst other, it's another 100 transits. So bottom line, in order to get to this final point, which, if you don't remember, relate to one of the 4 core science goals of Hubble, origins of life in the universe, we may have to spend 6 years to get to that point, at least. So it's many, many, many cycles. And we can stop at any point, right? If we don't find atmosphere, done. Like, just wait for the next generation of observatories. It's not worth spending more time. When I say don't find an atmosphere that's amenable to in-depth study with James Webb. If it's too thin or too cloudy, forget about it. It's not worth spending hundreds of transits on it. But still, bottom line, it's going to take many cycles. And if we don't start that discussion now, we may wake up at cycle 6 and be, oh, what were we doing with TRAPPIST-1 or a system like it? So that's the reason why I wanted to end with this point and take any question you may have. I don't know where we're at on time, but I think we're good. 10 minutes. Thank you.
Thank you, Julien. Are there any questions? Go ahead, Charles.
Yeah, I'm wondering how severe the opacity wall issue is for parameters that might be combinations of multiple species, for instance, C to O ratio. Should we be assuming a floor error on that that's much higher than what's usually reported?
Yeah, totally. And in fact, just earlier this week, there's an HG209 paper that was put online with a really tight constraint on C to O ratio, and they were kind enough to share all of this data, so we're going to work on providing an understanding of how sensitive the constraints that were placed are to this type of issues. Yeah. I mean, think about it, right? Each of these constituents, the one that are under the C ratio and the O ratio, or number densities, are affected by their own set of uncertainty rooted in their opacity models, how each of their underlying molecules, say, are affected by a lack of understanding or poor parametrization of their own broadening with the background gas, and there is no relating each. These are not correlated sets of uncertainty, right? So they add on instead of just mutually distracting one another.
Martin?
Yeah, I wondered what the scale of the calculations that have to be done to get rid of this problem, the quantum calculations.
Yeah, that's a great question. So,
how long is it going to take? How much money?
That's a great question. So, in terms of money, I think we need to make. Well, you can correct me on that, right?
Well, millions of dollars and millions of hours, basically. Yeah. Computational, yeah, but
Depends how many millions, because it's obviously a problem that's important to solve. So, a bunch of millions, yeah.
Yeah.
But if it's 100 million, then you may have a problem.
No. I mean, the good thing is the approach we're hoping to take leverage, computing facilities, and there's quite a few supercomputers around. That helps. What will be tricky, I think, is if we were to try to tackle this solely using lab measurement, that will be really expensive. And so moving towards a scalable infrastructure, both in terms of software and hardware, is going to be an investment over the next 6 months to a year. And then a system like CO2, H2, 6 months computation. A system that involves water or methane, that's going to be more, but hopefully as we move towards that infrastructure, we can keep on optimizing and maybe build the relevant hardware to do that efficiently. And then it's just about connecting with the labs that can provide us with a benchmark for a few of these TP.
yeah, it's scalable, basically, right? So, Charles?
So I was intrigued that you were including in your models notions of dark spots and factor. Do you assume solid body rotation for the star when you do this? Because on the sun, there's a very strong variation in rotation speed.
That is a great question. So in the
Sorry, can you repeat the question?
yeah, the question was to what extent do we account for differential rotation in our model? Right? It's a good summary of the question. In the current framework, we assume that it is indeed a solid body rotation. And so we're complexifying the model in order for us to understand what are the limitations of the framework. And so the performance I showed you, I cheated. Let's put it this way. The performance I show you here assume that we already have a pretty tight constraint on the latitudinal and longitudinal position of the spots. Because there's a degeneracy between fully retrieving these spectra empirically and their size and the position of the elements. So what we're moving towards now is building machine-learned hybrid prior, acknowledging the fact that there is a relationship between a wavelength and the other, not in a way that as constrained as trying to fit spectral model, but saying base level, the out-of-feature spectra should behave as a black body, right? And just starting to bring some physics-based information to constrain the relationship across wavelengths drastically allow you to constrain empirically the position and size of the spot. And so as we move toward that, we can start accounting for different topology, rotation structure, and so forth. So this is the next step, yeah.
There's another question there.
Another question about the stellar models. Do you all account for flares, the types of flares?
Great. So we do not, yeah, sorry, thanks for asking me. The question was, do we account for flares? And the answer is no. Also, in the TRAPPIST-1 data, we have basically one flare per transit. Well, maybe not. Let's say every 50% of the transit observation with James Webb have a flare in there. And so what we're hoping to do is to we're going to ask for full rotation of the star, and believe it or not, over the course of 3.3 days, which is the rotation period of the star, there are windows where we can get 9 transits bonus. That's how frequent transits are, so if we select well. And so what we're hoping to do is to have, over the course of a full rotation, about 20 flares. And then, owing to these 20 flares being observed, we can start using, and we get to see the lines and so forth. We're hoping to parameterize have this relationship between the lines and the amplitude, relative amplitude, and the actual blackbody temperature of each flares. So we can start moving towards a way to characterize and remove flares, even though we only see at times part of the flares when we do just transit windows. Does that make sense? Okay, I'm happy to talk more about that too.
Do we have any questions online? No? Okay, any more questions in the room? Okay, well, with that, let's thank Julien again. Thank you very much for this. And just a reminder, there is coffee and tea there, so if you want to hang around longer and talk to the speaker. Well, we're going to be 5 in the Royale, where it is.
Oh, it's on conference.
Yeah.
It's just past.
Just past Paradise.
Okay, on the same side?
I think it was
Oh, okay, it was on this side of